Hello everyone, welcome to this lecture. I am Amlan Das. Now I am going to discuss about X-ray diffraction and Bragg's law. Okay. After the discovery of X-ray, it was realized that X-ray was a kind of electromagnetic radiation with the wavelength much smaller than that of the visible radiation. We know that diffraction of ordinary visible light can be done with the help of diffraction grating. So, in the initial stage, attempts were made to produce diffraction of X-ray by ordinary optical grating. But it was not possible to diffract X-ray by ordinary optical grating. X-rays have wavelength of the order of angstrom, that is 10 to the power minus 10 meter. Okay. In 1912, a German physicist von Laue first pointed out that diffraction of X-ray could be performed more easily with the help of crystals. Okay. Now, in a crystal, atoms are arranged in a periodic manner. If we draw this, suppose this is an atom of the crystal, this is the second atom and this is the third atom. So, these are the atoms of the first layer of the crystal, and suppose these are the atoms of the second layer in a crystal, and these are the atoms of the third layer in a crystal. Okay. Now, the distance between two consecutive atoms, that is any two nearest neighboring atoms, is called interatomic spacing. And in a crystal, the interatomic spacing is of the order of angstrom, that is 10 to the power of the order of 10 to the power minus 10 meter. Okay. So, to explore the structure of the crystal, we require wavelength of incident wave comparable to the interatomic spacing. Okay. To explore the structure of the crystal, we require wavelength of incident wave comparable to the interatomic spacing of the crystal. Now, the periodic arrangement of atoms in a crystal behaves like a diffraction grating. Okay. The periodic arrangement of atoms in a crystal behaves as a diffraction grating. So, a crystal grating would behave like a three-dimensional space grating, and for this reason crystals are suitable for X-ray diffraction, and from this we can know many information about the crystal. Okay. Now, visible ray or ultraviolet rays have a longer wavelength than X-ray. Okay. Visible ray or ultraviolet ray have a longer wavelength than X-ray. So, they are not used for exploring the crystal structure at an atomic scale. On the other hand, gamma rays are not used to study the crystal structure because gamma rays have smaller wavelength than that of the X-ray. So, gamma rays are diffracted through very small angle which cannot be conveniently measured. Okay. So, X-rays are suitable to study the crystal structure. Okay. After that, two physicists, Frederick and Klipping, performed an experiment with the help of a zinc sulfide crystal to test the X-ray diffraction. Okay. Two physicists, Frederick and Knipping performed an experiment with the help of zinc sulfide crystal to test the X-ray diffraction. Now I discuss about Bragg's law. Okay, but before going to Bragg's law, I will discuss how a crystal diffracts X-rays. Okay, a crystal diffracts X-rays because X-rays are scattered elastically without change any wavelength by the charged particles of the atoms in a crystal. Okay. Now, suppose let us draw an atom of the crystal. Suppose this is the nucleus of the atom and these are the electrons revolving around the nucleus. Okay, this is the nucleus and these are the electrons revolving around the nucleus. Okay, now suppose a monochromatic beam of X-ray falls on an electron on an atom. Okay, so when a monochromatic beam of X-ray falls on an electron of an atom, the atomic electron starts to vibrate under the same frequency as that of the incident wave under the influence of the electric field vector of the radiation. Okay, so when a monochromatic beam of X-ray falls on an electron, the atomic electron starts to vibrate and these electrons are accelerated. Okay, and we know that accelerated charged particles emit radiation. So these accelerated electrons emit secondary radiation. Now this secondary radiation will spread out in all direction. Okay, this secondary radiation will spread out in all direction. Now these rays will interfere constructively or destructively according as the wave meet in the same or opposite phase and produce maxima and minima and undergo diffraction phenomena. Okay, so these rays will interfere constructively or destructively and produce diffraction phenomenon. So this is the process through which a crystal diffracts X-rays. Okay, now I discuss about Bragg's law. Okay, the famous British physicist W.L. Bragg. The famous British physicist W.L. Bragg suggested a very simple explanation for the production of Laue diffraction pattern. Okay. Now consider parallel planes. Suppose this is the first plane and these are the atoms. Okay, this is the first plane and these are the atoms. Suppose this is the second plane and these are the atoms, and this is the third plane and these are the atoms. So they are parallel planes. Suppose this point is P and this point is Q. Okay, and the planes are separated by a distance d, that is, this distance is d. So interatomic spacing is d. Now suppose a monochromatic beam AP, suppose a monochromatic beam AP of wavelength lambda is incident on an atom of the first plane at the point P, and after reflection, and here glancing angle is theta. Okay, so here a monochromatic beam of X-ray of wavelength lambda AP is incident on an atom at the point P of the first plane, and after reflection goes along, suppose, PB. Okay. Now suppose another parallel X-ray BQ. Okay. Another parallel X-ray BQ is incident on an atom of the second plane at the point Q at the same glancing angle theta, and after reflection goes along QD. Sorry, this point is, this is AB, and suppose this is CQ and QD. Okay, so these rays, so these are parallel rays. Okay, and a monochromatic X-ray AP is incident at the point P and goes along PB, and another parallel X-ray CQ is incident at the point Q and goes along QD. Now here this angle is theta, so this angle is also theta. Okay, now this distance is d, so this is d. Now we draw a perpendicular PL. Okay, we draw a perpendicular PL on CQ, and we also draw a perpendicular PM on QD. Okay, we draw a perpendicular PL on CQ, and we also draw a perpendicular PM on QD. Okay, so here PL is the incident wavefront and PM is the reflected wavefront. Okay, now it is clear that the ray reflected from the second plane travels an extra distance LQ plus QM. Okay, the ray reflected from the second plane travels an extra distance LQ plus QM. So here path difference is LQ plus QM. Okay, so here path difference equals to LQ plus QM. Now from the triangle from the triangle PLQ we see that this angle is theta. Okay, and this angle is 90 degree. Okay, this angle is theta and this angle is 90 degree. So this is 90 degree minus theta, and so this is 90 degree minus theta, and this angle is 90 degree. So this angle is theta. Okay, so this is theta. So this angle is theta and this angle is also theta. Similarly, this angle is theta and this angle is also theta. Okay. This angle is theta. So from the triangle PLQ, from the triangle PLQ we see that this distance is d. So here sin theta equals to LQ by PQ. Okay, sin theta equals to LQ by PQ. Now value of PQ is d, so this is equals to LQ by d. So here LQ equals to d sin theta. Okay, so from the triangle PLQ we get value of LQ is d sin theta. Now from the triangle PMQ, we see that this distance PQ is d. So here sin theta equals to QM by PQ. Okay, QM by PQ. Now here PQ is d, so this is equals to QM by d. So QM equals to d sin theta. Okay, so QM equals to d sin theta. So if we put the value of QL, LQ and QM, then we get the path difference equals to d sin theta plus d sin theta. This is equals to 2d sin theta. Okay, so total path difference is 2d sin theta. Now if this path difference is an integral multiple of lambda, then constructive interference will occur. Okay, so if this path difference is an integral multiple of lambda, then constructive interference will occur, and the intensity will be maximum if 2d sin theta equals to n lambda. Okay, the intensity will be maximum if 2d sin theta equals to n lambda. Here n equals to 1, 2, 3, etc. N is called order of diffraction. Okay, and this equation is called Bragg's equation or Bragg's law. So this equation is called Bragg's equation or Bragg's law. Now here we see that for n equals to 1 we get first order diffraction, for n equals to 2 we get second order diffraction, and so on. Okay, so 2d sin theta equals to n lambda, this is Bragg's law, and here lambda is the wavelength and n is the order of diffraction. Okay, now if we know the experimentally observed diffraction angle theta and the wavelength lambda, then the value of interatomic spacing d can be easily measured. Okay, easily calculated, and from this we can know many information about the crystal. Okay, thus we discuss X-ray diffraction and Bragg's law. Okay, thank you for watching this video.